momentum tensor. We studied the equations of motion, and we found that in the equations of motion, if we take the scalar dust and integrate, that the energy momentum tensor couples to the Christoffel symbol. And so there is a coupling, and we can see that the energy momentum tensor is relevant for the coupling to the Christoffel symbol. Now, in section 110, I want just shortly discuss how Einstein put the Maxwell equation in a parametric form in 1916. Maxwell's equations in parametric form, which means before the metric comes in parametric form, this is a whole movement which developed for quite some time. I will talk about this tomorrow at this conference a little bit more. If you, Einstein picked two field variables for Maxwell's equation. I mean the well-known field strength, which you know, Fij, which is the four-dimensional version for the fields, for the E field and the B field, the electric and the magnetic field. And he picked the excitation, that's the name of Sommerfeld and me, which is a tensor density in tensor analysis, which is from the D and the H field. Well, I have a lot of some different H's, so I have to be a little bit careful. I think I might be an H. The electric and the magnetic excitation. And then you can write, as most of you of course know, all of you know that the Maxwell equations can be written that the divergence of the excitation is the current and the curl of the field strength, which is EI of Fjk, totally anti-symmetric, is equal to 0. And in order to find vacuum electrodynamics, you have to link the excitation with the field strength by what is usually called a consecutive law. But if you are in vacuum, you have just Hij equals the square root epsilon 0 over mu 0 times the square root of the determinant minus determinant of G times the G I K times G KL times F KL. And this is how Einstein put it immediately shortly after he formulated general relativity in 1916. So you see the Maxwell equation, there is not the coupling to the gravitational field, to the Christoffel symbols, does not take place in Maxwell's equation. You don't have to substitute the partial by the covariant derivative, as is usually done, but the coupling with the gravitational field comes only in the linking equation, which links the H to the F. In exterior calculus, it's of course written E of H is equal to J. This is a 3 form, this is a 2 form, with twist, and this is a 2 form without twist, df equal to 0, and H is equal to the square root epsilon 0 over mu 0 times the whole star of F. So this is a formulation how you couple Maxwell's equation to the electromagnetic to the gravitational field. I think that's only a short reminder. Section 1.11. We discussed, of course, that by exploiting the equivalence principle and equation of motion, force-free motion, a particle under force-free motion, that the Christoffels are the same to gravitational field. And of course then we were able to show in Minkowski space the curvature tensor belonging to the Christoffels is 0, but if you have a real gravitational field under the Christoffels, you have already in a flat space-time in a curvilinear coordinate system, but if you have a really gravitational field, the Christoffels do not any longer fulfill the condition that the curvature is 0, so the curvature is set free, if you like, and you find then Einstein's field equation by the Einstein's field equation. You find by the usual methods. You have the curvature tensor, which for Christoffels we have a little, because later we have more general curvature tensors. I, J, K, L, these are definitions of Schouten and also Inter, for instance, the conventions. And you have the Ricci tensor, I, J, K, I is equal to Ricci tensor, which J, K, and here the curvature scalar, which is just the square root, the base of this. So R, this is here, it's just by definition, G, I, J, times the Ricci, I, J. And we have then the gravitational action, I is equal in integral, 4-dimensional integral, of d for x times the square root minus the determinant and times the Ricci scalar, and you have by the variational principle you find the Einstein field equation, which I J minus 1/2 G_I_J times the Ricci scalar minus, if you like, the cosmological constant lambda 0 times G_I_J is equal the energy momentum tensor minus kappa times, I take for symmetric energy momentum tensors small t, as we did already in the last lecture, and Tij is the Einstein equation. That's the second order equation, second order in G. So you have second derivatives then G, and it's linear in the second derivative, so it's a quasi-linear second order partial differential equation. It's of course a degenerate variational principle, because the curvature scalar itself is of second order, but the field equation turned out also to be of second order, but for which usually, if you have a second order variational principle, the field equations would be fourth order. And this is degenerate in that sense that this is not the case, and this can be shown that if you split off a divergence from the curvature scalar, then you can write it as an expression which is a square in the Christoffel symbols plus a divergence, and the Christoffel symbols are first order. The divergence doesn't play a role in the variation. The Christoffels are first order, and the field equation second order. So the world is okay again. So we understand this happening. Now, I don't add much more. General relativity has withstood all experimental tests in macrophysics, slowdown of the orbital period of the Hals-Taylor pulsar, is perhaps the most impressive scalar pulsar. I mean, I have the period 1975 until it was really proven. Of course, they now follow this period up to today, and it is with ever increasing accuracy. And this has proven Einstein's quadrupole formula, which is the formula for the emission of gravitational waves, which itself is a quadrupole formula, which is a certain percentage. So at least indirectly, gravitational waves are seen to be there. You don't see them directly, but indirectly you see there must be an emission of gravitational waves according to Einstein's quadrupole formula. So energy is lost, and so the pulsar speeds up, and this can be measured very accurately.
Okay, just give me comment. So there are other binary pulsars which also.
Sorry?
There are more binary pulsars.
Yes, of course. I mean, there are now with better and higher nonlinearities. I mean, there are papers by, I recall, Kramer et al. This is the most recent pulsars, which are much better. I just remember one of the principal investigators. It's in Manchester. He's now in Bonn, I think.
And they are not better yet, but they will be better because they are closer.
Yes, no, I thought they are already better yet. But maybe you are right, I'm not sure.
It's not for the moment, but one of the pulsar, they accrue dipole radiation better
Then for the
Taylor.
Okay.
Okay.
So in any case, I think we agree that the experimental, I mean the order of magnitude general relativity has proven is perhaps a 0.1%, something like that, you know. It's not, I mean, the light deflection, all these things is all this order of magnitude. Questions? So this was just the end of my first lecture, the first double lecture, where I discussed from special to general relativity how this took part. And in the second part, which I want to start now, it's called analyzing general relativity theory. I mean, the progress which took part, I think I can wipe out this now. Now we are, of course, I mean, I'm not as advanced as teleparallelism theories and dark matter and things like that. I'm still 100 years back in time. So, I mean, so you may consider that to be a very anachronistic undertaking. But I mean, I take what our seminar speaker has said. I think that one has to take it very seriously, that one can either believe there is dark matter, or one can believe that Einstein's theory has to be changed. I mean, and nobody knows for sure, but people who always at the beginning of their lecture show me in these diagrams how many dark matter, etc., etc. I think I'm a bit sick of that, because I mean, it always supposes that general relativity is correct, which of course I'm a relativist. I like the theory very much, and I've done some work, I think, and I would also, and so this is an assumption. But at the same time, it's already assumed that there is inflation, and inflation requires a scalar field. So you changed general relativity already. Otherwise, there would be not the inflationary phase. So, in fact, people change general relativity, and this scalar field is totally ad hoc. It's just introduced in order to fulfill a certain purpose. Now, so there is good reason to believe that perhaps we should have a principle which selects a gravitational theory which goes beyond general relativity. Such a principle, of course, has to be formulated in such a way that general relativity is in a certain limit valid. We know that, of course. Also, Newton's theory is valid in a certain limit of general relativity. And Newton's theory is a beautiful theory. We all know that, and we know that general relativity. Following work of Sciarra and Kibble, I believe that the gauge principle is a very powerful principle, and one should try to change perhaps gravitational theory and apply gauge principles which were so successful in physics. So this is a motivation. So one of the theories which was investigated, the Poincaré gauge theory, the torsion mode for instance, was investigated by Xie, Nestor, and Yo, and Geng here, Professor Geng has written a paper on this also. There you have a torsion mode which is a scalar, right? I mean, so you can produce scalars in the Poincaré gauge field theory, not only one, and you can look for the consistency of such theories, and that's exactly what they were looking in these two papers with Geng and Zheng and Li, I think, is the third one. So and for understanding what could be the principle, and I opt for the gauge principle as one possibility, perhaps there are other possibilities, is that one understands what happened to general relativity. And people who analyzed general relativity, this started, as we now will see, right at the beginning of, in the middle of 1960, and already before general relativity was formulated, people began to wonder. Chapter 2. Analyzing general relativity theory. Okay, so let us follow the historical roots of this analysis. And of course, the development of differential geometry as a mathematical discipline after the discovery of general relativity was enormous. So it has an enormous impact on differential geometry. But one has also to recognize, of course, that Einstein took tensor calculus and this from mathematics. He had to learn it because he didn't know that. So before general relativity was introduced, a certain activity in differential geometry took place, and the physicists didn't notice that until Grossmann came, a colleague of Einstein, and told Einstein about this calculus, and he used it. And so differential geometry hit physics at this time, but physics hit back and posed a lot of questions which were then solved by mathematicians. So there is always this interaction between mathematics and physics, which is very useful. And sometimes one field is more more advanced, and sometimes the other field. It's always one way or the other. But before I make this, I make remarks because I know that this is often not considered seriously. Remarks. These are only remarks on coordinates and frames, on coordinates and frames. And on tensor and the tensor algebra. Of course, I cannot be a tensor algebra. I just make some general statements and exterior differential forms, exterior differential forms. Just these are tools which physicists use in general relativity inter alia, and one has to be aware of this. And this we have curvilinear coordinates. Let us start with curvilinear coordinates. Curvilinear coordinates. Xi 0 till x3. These are curvilinear coordinates in space-time. Now, if you have curvilinear coordinates, you can suppress one dimension, so you can you can draw coordinate lines. So that's this coordinate line x1, and this coordinate line x2, and this coordinate. This is where this x1, x2, or x3 is constant. And then you can introduce at one point of the manifold tangent vectors, which in mathematics are often just partial I, partial 1 in the one direction, partial 2, well, this point is so good. And in the 3 direction we have here. And these are called natural frames. Why natural? Because they can be constructed from tangent vectors which go along coordinate lines. And so these are natural frames, or coordinate frames, natural frames. And they consist in 4 dimensions of 4 vectors. And each vector has 4 components. This corresponds to 60 components. Okay, so instead, so this, and you have for each such frame, you have a dual frame, which is called a co-frame. Dual to it, you have a co-frame. These are 4 covectors. Covectors are also called one-forms. Covectors or one-forms. So you have 16 components. This is just the 4 times 4 matrix. You compute the reciprocal of this 4 times 4 matrix, and you get the confluence. So, and now what you now do, and you can get rid of this naturalness. You just, this is in a manifold, linearly independent frame, and by linear combination you can transform it to another frame. I cannot draw it now, it's you know what a linear combination is. So out of you can build...
Sorry.
Yes?
4 vectors, 16 components. But surely, since you've drawn these as special components, special vectors, they must be the vectors 1, 0, 0, 0.
Yes,
yeah,
yes.
and so okay, so almost all the components are 0.
Yes,
basically.
that's right.
Okay.
That's right. So I mean, here you have in 4 dimensions 0, 1, 0, 0, 0, etc. Yes.
Yeah.
Yes.
Okay.
So if you have now build a linear combination of a natural frame, you get an arbitrary frame, let me call it arbitrary frame. And these are 4 vectors. I do not denote it by an arrow. Let me make it here a little bit thicker. And this you can decompose with respect to this natural frame. This is E, the conventions I use, I at the first position, alpha at the second, times partial I. So here are the, of this frame the 16 components. And if you take the co-frame, which I denote by theta, these are the one forms. Let me call it here beta, for reasons which become evident. Then you can also decompose it, and usually it's also called E. You could call it theta, but usually the convention is to call it B anyways, times J beta times